I'm Dr. D.K. Tripathi, an assistant professor of physics under the Department of Basic Science and Humanities. So we were studying the statistical mechanics, and this is the third lecture where we will discuss the assumptions of the three statistics. The three statistics we have seen, their names are Maxwell-Boltzmann statistics based on the classical mechanics, and the two other quantum statistics based on the quantum theory, that is Fermi-Dirac statistics as well as the Bose-Einstein statistics. Now you see, those particles which used to follow the Maxwell-Boltzmann statistics are called as Boltzons, and those particles which used to follow the Fermi-Dirac statistics are called as fermions, and the particles which used to follow the Bose-Einstein statistics are called as bosons. So these are their names. Now let us discuss the assumptions of three statistics. Okay, so when we are going to assume something to develop a theory, there must be some basis of the assumptions. The assumptions must have some clarification. Without clarification or without any base, we cannot take any assumption. So the first basis of assumption is distinguishability of the particle. Distinguishability of the particle means in a pool of particle or in an assembly of particle. Just recall in the first class I told you the assembly of particle ensemble. So in an ensemble of particles, what is the behavior of the particles which you are going to consider? Are they distinguishable in that very pool of particles, or they are indistinguishable? That means, can you recognize them or you cannot recognize them? So on the basis of that, on this basis, the assumptions are taken in all three statistics. Now, Maxwell and Boltzmann has taken that bosons are distinguishable in nature. Distinguishable in nature means these particles can be distinguished in a pool of particles. That means if two bosons are there, you will be able to distinguish them. Okay, this means that their name will be different. Now, about in the Fermi-Dirac statistics, the assumption in the Fermi-Dirac statistics is that fermions are indistinguishable in nature. That means they cannot be identified in a pool of particles. In an ensemble, you cannot identify the fermion. That means suppose there is a pool of particles and all the particles are if in random motion. You want to suppose at a instant of time t1, you have seen this particle. After some 5 second or 7 second, if particles are in random motion, you will not be able to recognize that which particle you have seen 5 minutes earlier, 5 seconds earlier. So fermions are indistinguishable in nature. They cannot be distinguished. Why? Because they are alike. They are alike, and that is why they cannot be distinguished. Bosons are also indistinguishable in nature because of their alike nature. That means in the pool of particles, all bosons are same. They all are having the same appearance or same characteristics, and that is why you will not be able to recognize that which boson you have seen earlier. Okay, so these are the assumptions. This means that if you are told to take 3 bosons by yourself, so you cannot take all bosons as A or B. The name of the bosons will be different. If you are taking one as boson A, then other boson will be B and third boson will be C. They must be different so that you can distinguish that A is different than B and B is different than C, because A, B, C are different things, not the same thing. Whereas if you are told to take 3 fermions, what you will take? You will take all of them as A, or all of them as B, or all of them as C, and same for the bosons. Now the second basis is number of particles. On the basis of number of particles, the assumption in all three statistics is, in Maxwell-Boltzmann statistics, number of particles are constant. That means if you are discussing a pool of particle or an ensemble of particles or a collection of particles, then what Maxwell-Boltzmann have taken as the assumption, that is number of particles are constant. Why? Because if you will apply the Maxwell-Boltzmann distribution function to know all the physical variables as Helmholtz free energy, partition function, temperature, all these physical variables, you will get the same. But if suppose you are adding some particles, so if you are adding the particles during the application of this Maxwell-Boltzmann statistics, then what you are calculating, that is based on the earlier number. Now you are increasing the particles. So when particle will increase there, then the energy of the total ensemble will increase. And because of that, there will be redistribution of energy. Due to that, what you will calculate as Gibbs free energy or Helmholtz free energy or temperature, that will be different than the calculated by the formula. Or if you are taking out some of the particles, so particles will come with their energy, and when the particles will come out with their energy, then there will be redistribution of energy in the pool of the particles. So because of that, the value of all the variables which you have calculated, that will be different. So that is why it is assumed that during the application of Maxwell-Boltzmann statistics, the number of particles are to be kept constant in the ensemble. Fermi and Dirac also have assumed the same thing with the same claim that if we extract out the particles or we add up the particle, then the energy will be redistributed, and because of that, what will be calculated with the help of this Fermi-Dirac statistics will not be exact one. Bose and Einstein also have assumed the same thing, that number of particles would be kept constant. Now, the third basis of assumption is total energy of the system. Total energy of the system, that means total energy of the ensemble. So what it should be? Now, just we have discussed that total energy of the system should be kept constant. Because if you are giving the energy from outside or if you are extracting the energy, then there will be redistribution of energy in the system. And if there will be redistribution of energy, then what will happen? What you will calculate, all the physical variables which you will calculate from the formula imposed by Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein will not be exact one. That will be different than the present physical situation. So just to have the same value as the ensemble is having, we will have to keep the total energy of the system as constant in the three statistics. Now about the quantum rules, there are 4 fundamental quantum rules. So this Maxwell-Boltzmann statistics is a classical statistics. So quantum rules are not applicable to Maxwell-Boltzmann statistics. Okay, whereas Fermi-Dirac statistics and Bose-Einstein statistics are quantum statistics. So Fermi and Dirac has assumed that all quantum rules are obeyed by fermions. What does this mean? That fermions used to obey all the quantum rules of Bohr principle, Hund's rule of maximum multiplicity, Pauli's exclusion principle. All these are obeyed by fermions. Whereas bosons are following all rules except the Pauli's exclusion principle. Bosons are not following the Pauli's exclusion principle. What is Pauli's exclusion principle? Pauli's exclusion principle is that no two particle will have all set of 4 quantum numbers same. There may be the 2 particles which are having the same principal quantum number, same azimuthal quantum number, same magnetic quantum number, but the 4th one, spin quantum number, must not be same. Why? Because if particles are having the same all 4 quantum numbers, this means both of these particles are residing at the same place, same energy state, which is forbidden in the Fermi-Dirac statistics. Whereas in Bose-Einstein statistics, he is saying that Pauli's exclusion principle is not obeyed. That means Bose have allowed that there may be two particles which can have the same quantum state, and this was one of the serious cause of rejection of Bose statistics. Probably all of you have heard about Bose. He was Satyendranath Bose. He has got 110 marks out of 100 in mathematics, and that was published by local dailies at that time, and later on the mark was synchronized to 100 by the head examiner. So he was very good scientist. You can say that actually what he did, he has done MSc from Presidency College, and after that he did some research work at Calcutta University, and later on he joined at Dhaka University. At Dhaka University, he has published, he was trying to publish this paper. He has written the paper when he was at Dhaka University. So he has taken bosons do not obey Pauli's exclusion principle. And when his paper was sent to the Royal Society, then Royal Society was having this objection that if you are saying that your statistics is quantum statistics, why it is not following the fundamental law of quantum theory, that is Pauli's exclusion principle? It must obey that. Later on, working with the Einstein, he has cleared all these things. Now, spin. So you see here, bosons do not obey Pauli's exclusion principle. That means in a single energy state, more than one particle can be put. And this is similar to the classical statistics, because in the classical statistics also, any number of particles can be put in one energy state. Now, spin. Spin is the next basis. Spin means orientation, orientation of the particle. Now, you see, in Maxwell-Boltzmann statistics is a classical statistics. So no quantum rule is applicable to it. So no quantization is applicable to it. And that is why they don't have any spin concept. So we can say that bosons are spinless. But Fermi and Dirac have assumed that fermions have half integral spin quantum number. Half integral spin quantum number means the spin quantum number will be n plus minus half h cross. So if you put n equal to 0, so what will be the spin quantum number? Plus half h cross and minus half h cross. H cross is what? Dirac's constant or reduced Planck's constant, because h cross is equal to h by 2 pi. Now h by 2 pi means Planck constant is reduced by a factor 2 pi. That is why this is called as the reduced Planck's constant. Someone is telling this as h cut. So h cross may be called, this may be called as h cross, and this h cross was introduced by at first Dirac. This Dirac, who has given the idea of Fermi-Dirac statistics. You see, one thing also I should say to you that Fermi and Dirac, both of them has worked out this statistics with the full effort. No one have given the less effort, but as Fermi was senior to Dirac, so Dirac told that the particle should be called as fermion. So from there we can learn that we should always honor our seniors. So fermions have half integral spin quantum number. Okay. Now Bose has assumed that bosons have 0 or full integral spin quantum number. Bosons may have 0 quantum number, or it may have full integral spin quantum number. Full integral spin quantum number means n plus minus h cross. So if n is equal to 0, then plus 1 h cross minus 1 h cross. Okay, so this was the Bohr's idea. Now if suppose n equal to 1, then 1 plus 1, 2 h cross, and 1 minus 1, 0 h cross. That is why bosons have 0 quantum number. may have spin quantum number. So spin of the bosons may be 0 or full integral spin quantum number. This is assumption made by Bose, Satyendranath Bose. You see, probably all of you have heard about that, that when the freedom struggle was going on, at the same time, India was also struggling for science. The English person were not trying to have the root of science in India, whereas three very, very good scientists of India who has enlightened the, you can say that light of science in India. First was Sir C.V. Raman, second was Professor Satyendranath Bose, and third was Jagdish Chandra Bosu. So, Sir Jagdish Chandra Bosu. So, these three were trying to enlighten the lamp of science in India, and later on, or you can say that at the same time, it was carried out by Meghnad Saha. So, these four great people of India who has worked for India, they secretly, if you learn the history of science at that time, you will find that these three persons, that is Meghnad Saha, C.V. Raman, and Satyendranath Bose, was having a meeting secretly, and they told that we should uh, fight for the freedom but using the science. Probably all of you have heard that when Professor C.V. Raman was Professor C.V. Raman was the professor, was made professor by Sir Asutosh Mukherjee at Calcutta University. So when Professor C.V. Raman was finding the Nobel Prize, at that time he cried at the stage, told that I am belonging to a country where I don't have badge on my chair of my own country. I am using the badge of Britain. So how they were thinking about the struggle, they were not like that. They were just having, they becomes deep on the freedom struggle. They were trying to have the struggle of, you can say that by brooming the science in the people of India. So bosons have zero or full integral spin quantum number. Wave function. Wave function is what? Wave function is the uh, function, or you can say that wave function is a function which is assigned to each and every particle of the ensemble, solution of which gives the space and time behavior of the particle. So it is very, very fundamental thing. And in the quantum mechanics, this is assigned to each and every particle. On the basis of that, the state of the particle can be told. So in Maxwell-Boltzmann statistics is a statistical is a classical statistics. That is why wave function is not assigned to it. No wave function concept is there. Whereas fermions, in the Fermi Dirac statistics, it was assumed that fermions have anti-symmetric wave function. Probably TKM sir has taught you symmetric and anti-symmetric wave functions. Suppose a particle whose wave function is given by psi1, which depends on x1, y1, z1 at time t1, and another particle whose wave function is given by psi2 at positions x2, y2, z2 at time t2. Okay, now suppose a particle in the coordinate system. Suppose this is a particle in the coordinate system. This is x-axis, this is y-axis. Okay, this is x-axis, this is y-axis, and there will be axis along the z direction. So if the three axes are there, suppose this particle is here. If this particle is here, then if its positions can be given as x1, y1, z1 at time t1. After some time, if this particle came here, what will be its wave function? Wave function will certainly be changed. Suppose the wave function is psi2. this will be equal to x2, and y1 will become y2. So y2, z2 at time t2. Now what we'll find? That x1 and x2 are same. y1 is equal to minus y2. This length becomes in the reverse direction. And z1 is equal to z2. So what we conclude? That particle is replaced by the same distance along the y direction below the x-axis. So if psi1 is equal to psi2, what we will call? We will call that the wave functions are symmetric in nature. Okay, that means with the change of the sign or with the displacement of the particle, if the wave function remains same, then it is called as symmetrical. But if psi1 is equal to minus psi2, what does this mean? This means that psi1 and psi2 are having the same magnitude, but the direction is different. If direction is different, this means that the wave functions are anti-symmetric to. So the examples of Maxwell-Boltzmann statistics, that means Boltzons are um, molecules of uh, uh, any gas, okay, at high pressure. The examples of fermions are electron, proton, other half integral spin quantum number particles. And the examples of bosons are photons, phonons, all of these. Now, let us try to find out that what are the characteristics of Boltzons. How Boltzons are behaving, what are their characteristics. So Boltzons are distinguishable in nature, we have seen. They do not follow any quantum rule because these are classical particles. So they do not follow any quantum rule. And more than one number of particle can be put in any energy state because Pauli's exclusion principle is not applicable there. And Boltzons are spinless. They don't have any spin. Spin concept is not there. Now, examples of Boltzons are molecules of gas at higher pressure. Now, fermions. What are fermions? What are the characteristics of fermions? We want to know that. Fermions are indistinguishable in nature. They cannot be distinguished. All quantum rules are obeyed by fermions. Fermions have half integral spin quantum number. Their spin quantum number is half integral. Fermions have anti-symmetric wave function. That means their wave functions does not remain same with the translation of the axis. And the examples of fermions are electrons, protons, neutrons, quarks, neutrinos. These all are the fermions. Now next is characteristics of bosons. What are bosons? What are their characteristics? Because these are very new thing to us. This Bose-Einstein statistics have given us the fifth state of matter. You know that there are three states of matter. You have learned this at school level, solid, liquid and gases. Fourth was plasma state. And on the basis of Bose-Einstein statistics, the fifth state of matter was discovered, that is Bose-Einstein condensate. And it is believed that this Bose-Einstein statistics is going to give the clue of nature. How the nature was built up where the energy goes. This is expected. And probably all of you have heard that in 2012, Higgs boson was realized in Large Hadron Collider experiment at Geneva. So bosons. Bosons are indistinguishable in nature. Bosons do not obey Pauli's exclusion principle. That is, more than one particle can be put in an energy state. Bosons have zero or full integral spin quantum number. Bosons have symmetric wave function. Examples of bosons are photons, helium atoms, gluons, phonons. So these are the examples of bosons. Now, these are the references which you must follow to understand this subject in better sense. Because Bose-Einstein statistics, Bose-Einstein statistics is most remarkable statistics in the history of science. So lastly, I thank all of you. Thank you.